Picture the universe not as a crowded sea of stars, but as a vast, intricate web, with galaxies strung like beads on invisible threads. Now imagine a hole in that web, a gap so enormous it could fit thousands of Milky Ways side by side with room to spare. This isn't science fiction, it's real. Astronomers call it the Great Void, a cosmic mystery so baffling it challenges everything we think we know about space. Stretching over 330 million light-years, this emptiness defies explanation. How can a region of the universe, teeming with the potential for galaxies, be so utterly blank? What kind of force could carve out a bubble of nothingness on such an unimaginable scale? The discovery of the Great Void didn't just puzzle scientists, it shook the foundations of modern cosmology. For centuries, we've assumed the universe was more or less evenly sprinkled with matter, with only small pockets of emptiness here and there. But this void is different. It's not just a gap, it's a cosmic anomaly, a ghostly fingerprint left by something we don't yet understand. Was it a collision with another universe, a burst of dark energy so powerful it swept matter away like a cosmic broom? Or is it a flaw in our understanding of the universe itself, a clue that the rules we've written might need rewriting? Today, we're going on a journey into the heart of this mystery. We'll explore the mind-bending theories that attempt to explain the Great Void, from the cutting edge of multiverse physics to the shadowy influence of dark energy. We'll meet the astronomers who first stumbled upon this cosmic oddity and the tools they used to uncover it. And most importantly, we'll ask what this void means for our place in the universe. Because if there's one thing the Great Void teaches us, it's that space is stranger, more unpredictable, and more wondrous than we ever imagined. By the time we're done, you won't just see the night sky the same way again, you'll feel it, a vast and mysterious frontier waiting to be explored. So let's begin. In 1981, astronomer Robert Kirshner and his team were mapping the distant universe, searching for patterns in the distribution of galaxies. What they found in the constellation Boötes wasn't just unexpected, it was unprecedented. Instead of the usual clusters and filaments of galaxies, their instruments revealed a staggering emptiness, a void so vast it defied logic. This wasn't a small pocket of nothingness. It stretched over 330 million light-years, a cosmic desert so large it could swallow thousands of Milky Ways without a trace. At first, the team thought there must be some error in their data. How could a region of space in a universe packed with billions of galaxies be so utterly empty? The key to their discovery lay in redshift surveys, a technique that measures how light from distant galaxies stretches as the universe expands. By analyzing the light's shift toward redder wavelengths, astronomers can calculate distances and map the universe's three-dimensional structure. When Kirshner's team pieced together their observations, they realized they weren't just seeing a gap. They were staring into one of the largest structures ever detected. The Great Void, as it came to be known, wasn't merely empty. It was a cosmic anomaly, a place where the rules of galaxy formation seemed to have been rewritten. The scientific community was stunned. For decades, astronomers had assumed the universe was relatively uniform on large scales, with matter distributed fairly evenly. But the Great Void shattered that assumption. It was like finding a hole in a piece of fabric, only to realize the hole was the size of a continent. Some researchers scrambled to recheck their own data, while others began questioning long-held theories about how the cosmos evolved. Could dark energy have pushed matter away? Was there some ancient cataclysmic event that cleared this region? Or was it simply a statistical fluke, a 1 in a trillion chance that left this pocket of the universe barren? What made the discovery even more remarkable was the sheer audacity of the void scale. Most cosmic voids are around 100 million light-years across, still enormous but manageable within existing models. The Great Void was more than 3 times that size, a yawning chasm in the cosmic web. It forced astronomers to confront an uncomfortable truth. The universe might be far stranger, far more unpredictable than they had ever imagined. And as we'll see, this was just the beginning of the mystery. Cosmic voids are like the empty rooms in the grand mansion of the universe, vast regions where galaxies are few and far between, leaving behind stretches of near nothingness. Picture a sponge with its intricate network of holes and solid material. The universe works in a similar way, where galaxies cluster along filaments and walls, while the spaces between them form these enormous voids. Most of these empty regions span around 100 million light-years, big enough to fit thousands of galaxies, but still fitting within the expected patterns of cosmic structure. Then there's the Great Void, an absolute titan among them, stretching over 330 million light-years. To put that into perspective, if you could travel at the speed of light, it would take you more than 300 million years just to cross this emptiness. That's not just a gap, it's a staggering anomaly, earning it the title of a supervoid, a classification reserved for the rarest and most extreme cosmic structures. What makes the Great Void truly baffling isn't just its size, it's the way it defies the usual rules of cosmic evolution. In most voids, you'd still find a handful of galaxies scattered here and there, like lonely outposts in a desert. But the Great Void is different. It's not just sparsely populated, it's almost completely barren, with only a tiny fraction of the galaxies you'd expect to find in a space that large. It's as if someone took a cosmic eraser and scrubbed away nearly all the matter in this region. Scientists have spent decades trying to understand how could nature produce something so empty on such an enormous scale. One clue lies in the cosmic web, the large-scale structure of the universe shaped by gravity and dark matter. Think of it like a colossal spider's web, with galaxies clinging to the strands and voids forming the gaps between them. Normally, these voids are part of a balanced system, where matter flows along filaments and collects into clusters, but the Great Void seems to break that balance. Its sheer size suggests something unusual happened during the universe's early formation, maybe a massive surge of dark energy, or a collision with another bubble of spacetime. Some researchers even speculate it could be a rare statistical fluke, a cosmic lottery where, against all odds, matter just didn't end up here. The Great Void isn't just a curiosity, it's a challenge to our fundamental understanding of how the universe works. If voids are the natural low-density regions of the cosmic web, then this supervoid pushes the limits of what natural even means. It forces astronomers to ask whether our models of cosmic evolution are missing something crucial. Could there be forces at play we haven't discovered yet? Or is this void a hint that the universe is far more uneven, far more unpredictable than we ever imagined? Whatever the answer, one thing is certain: the Great Void isn't just an empty space. It's a cosmic mystery waiting to be solved. Imagine the universe as a colossal spider's web, shimmering across billions of light-years. Galaxies don't float randomly through space, they cling to vast, twisting filaments, forming an interconnected cosmic tapestry. This is the cosmic web, the scaffolding of the universe, where dark matter and gravity pull matter into dense clusters and leave behind immense, empty voids. It's a delicate balance, like foam on the surface of an ocean, with galaxies gathering along the bubble's edges and emptiness stretching between them. But the Great Void doesn't just fit into this pattern, it shatters it. Its staggering size hints at a disruption in the web's design, as if a cosmic hand reached in and tore a hole through the fabric of space itself. To map this web, astronomers use tools like redshift surveys and gravitational lensing, piecing together the universe's structure in 3 dimensions. Think of it like reconstructing a city's skyline using only shadows, except the shadows stretch across millions of light years. By tracking how galaxies cluster and how light bends around invisible masses, scientists can trace the unseen threads of dark matter that hold everything together. These maps reveal a universe far more structured than we once believed, with galaxies strung along filaments like pearls on a necklace. But when they reach the Great Void, the pattern breaks. Instead of the expected sparse scattering of galaxies, there's almost nothing, a blank spot in the cosmic blueprint. What could cause such a gap? One possibility lies in the early universe, when tiny quantum fluctuations during inflation. The rapid expansion just after the Big Bang were stretched to enormous scales. These fluctuations seeded the cosmic web, with denser regions collapsing into galaxies and emptier ones growing into voids. But the Great Void's size suggests something extraordinary. Perhaps a rare, ultra-low-density fluctuation grew unchecked, ballooning into this vast emptiness. Or maybe dark energy, the mysterious force accelerating the universe's expansion, played a role. If dark energy isn't perfectly uniform, localized surges could have pushed matter away, leaving behind this colossal bubble of nothingness. Then there's the multiverse angle. Some theorists propose that the Great Void could be a scar from a collision with another universe in the multiverse, a bubble of space-time that briefly brushed against ours, sweeping matter aside like a cosmic tide. It's a wild idea, but not impossible. If other universes exist beyond our own, their interactions might leave behind signatures like this void, of course, proving it is another matter. For now, the Great Void remains a puzzle, a silent challenge to our understanding of the cosmos. What makes this even more fascinating is how the void distorts our view of the universe. Light traveling through it behaves differently, subtly shifting in ways that reveal the void's gravitational influence. It's like looking through a funhouse mirror, except the mirror is 330 million light-years wide. These distortions, known as the integrated sachs-wolfe effect, offer clues about the void's origins, but they also complicate things. The void's sheer size means it could be skewing our measurements of cosmic expansion, making the universe seem to grow faster or slower than it really is in this region. The cosmic web is more than just a map. It's a record of the universe's history, written in galaxies and emptiness. And the Great Void, it's a chapter we're still learning to read. Whether it's a remnant of inflation, a fingerprint of dark energy, or evidence of a multiverse, one thing is clear: this void isn't just empty space. It's a window into the forces that shape the cosmos, and a reminder that the universe still holds secrets we've only begun to uncover. One of the most mind-bending explanations for the Great Void comes straight from the cutting edge of theoretical physics, the multiverse. Picture this: in the infinite foam of bubble universes, each with its own laws of physics, one of these cosmic pockets might have brushed against ours in the distant past. This collision wouldn't have been a catastrophic crash, but more like two soap bubbles gently nudging each other. The energy from that interaction could have pushed matter away from the contact point, clearing out an enormous region of space and leaving behind the void we see today. It's a radical idea, but not impossible. The math of inflationary cosmology actually allows for such collisions, and if they happened, the Great Void might be the ghostly fingerprint of that encounter. But here's the catch proving it. Unlike a car crash where skid marks and debris tell the story, a collision between universes would leave far subtler clues. Some researchers look for patterns in the cosmic microwave background, the afterglow of the Big Bang, searching for unusual temperature fluctuations that might hint at such an event. Others simulate these collisions in supercomputers, trying to match the void's properties to theoretical predictions. So far, no smoking gun has been found, but the multiverse theory remains one of the most tantalizing explanations for why this void exists. Then there's dark energy, the mysterious force accelerating the universe's expansion. Normally, dark energy is thought to act uniformly, gently stretching space everywhere. But what if it isn't perfectly even? Imagine a patch of space where dark energy briefly surged, like a wave cresting in the cosmic ocean. That surge could have pushed galaxies away, clearing out matter and leaving behind the great void. This idea ties into a broader mystery: why dark energy seems so constant now, when in the past it might have fluctuated wildly. If those fluctuations were powerful enough, they could have sculpted voids on scales we're only beginning to comprehend. Of course, not everyone buys into these exotic explanations. Some cosmologists argue the Great Void might just be a statistical fluke, a rare but inevitable gap in the cosmic web. Think of it like rolling dice. If you do it enough times, eventually you'll get a string of ones. In a universe as vast as ours, even the unlikeliest configurations can emerge purely by chance. The problem with this view is scale. Most cosmic voids are around 100 million light-years wide, but the Great Void is more than 3 times that size. The odds of such a massive emptiness forming randomly are astronomically low, so low that many scientists suspect something more fundamental must be at work. Each of these theories has its strengths and weaknesses. The multiverse angle is thrilling but hard to test. Dark energy fluctuations fit within known physics, but require assumptions about its behavior we can't yet verify. And while the statistical fluke explanation is simple, it feels unsatisfying for something so extreme. What's fascinating is how the Great Void forces us to confront the limits of our knowledge. Whether it's evidence of a multiverse, a dark energy anomaly, or just a cosmic roll of the dice, this void reminds us that the universe still holds mysteries beyond our current understanding. And that's what makes it so compelling, not just as a scientific puzzle, but as a window into the unknown. Dark energy is the universe's greatest enigma, an invisible force stretching space itself apart, pushing galaxies away from one another faster and faster with each passing moment. We know it makes up about 68% of the universe's energy content, and yet we still don't understand what it truly is. Now, scientists are asking an even more provocative question: could this mysterious force be the architect behind the Great Void? The standard view of dark energy paints it as a smooth, uniform presence, like an unseen mist filling every corner of the cosmos. But what if it isn't so even? Imagine dark energy as a restless ocean, with waves and ripples that vary in strength from place to place. In one region, a powerful surge might have pushed matter outward with extraordinary force, clearing out galaxies like a cosmic tide receding from shore. Over billions of years, that outward push could have left behind the staggering emptiness we now call the Great Void. This idea, known as inhomogeneous dark energy, suggests that dark energy's influence isn't constant. It might have peaks and valleys, with the void marking one of its most dramatic low points. There's a catch, though. If dark energy fluctuated enough to carve out a void this size, why don't we see more of them? The Great Void is a rare outlier, which either means such fluctuations are extraordinarily uncommon, or our understanding of dark energy is missing something fundamental. Some theorists propose that dark energy's behavior in the early universe was wildly different from today. Perhaps it went through phases of intense activity, like a geyser erupting in fits and starts. If one of those surges happened in just the right place at the right time, it could have set the stage for the void's formation. Then there's the counter-argument. Maybe the void isn't a product of dark energy at all, but a challenge to it. The standard model of cosmology, which relies heavily on dark energy to explain the universe's expansion, predicts a certain distribution of matter and voids. The Great Void, with its extreme size and emptiness, strains those predictions. Could it be evidence that dark energy doesn't work the way we think, or worse, that our entire framework for understanding cosmic expansion needs a rethink? One tantalizing clue comes from the void's effect on light. As photons from the cosmic microwave background pass through the Great Void, they lose a tiny amount of energy, a phenomenon called the integrated sachs-wolfe effect. This subtle shift could hint at the void's gravitational pull, or lack thereof, offering indirect evidence of dark energy's role. If dark energy truly cleared out this region, the void's gravitational footprint should reflect that. But the data isn't conclusive yet. Some measurements align with dark energy models, while others seem to contradict them, leaving scientists in a fascinating debate. What's clear is that the Great Void isn't just a curiosity, it's a stress test for our theories. Whether dark energy sculpted it, or its existence forces us to rewrite the rules, this cosmic emptiness is more than a blank space. It's a question written in the fabric of the universe, waiting for an answer. And as telescopes grow more powerful and simulations more precise, we might finally uncover whether dark energy holds the key, or if the void is pointing us toward something even stranger. The universe isn't just expanding, it's doing so at an accelerating rate, a phenomenon driven by dark energy. But what happens when you measure that expansion from inside a cosmic desert like the Great Void? Suddenly, the numbers don't add up. The Hubble constant, which quantifies how fast the universe is growing, has been a source of fiery debate among cosmologists. Some measurements, like those based on the cosmic microwave background, suggest one value. Others, like observations of nearby supernova, suggest another. This discrepancy, known as the Hubble tension, might have an unexpected culprit, the Great Void's staggering emptiness. Here's why. The Hubble constant relies on tracking how quickly galaxies move away from us, but that motion isn't uniform across the cosmos. In dense regions, gravity tugs galaxies together, slowing their apparent recession. In voids, the lack of matter means less gravitational resistance, so galaxies here appear to flee faster. Now picture Earth sitting near the edge of the Great Void, a 330 million light-year wide bubble of near-nothingness. If we're measuring expansion from this lopsided vantage point, our local, empty neighborhood could be skewing the results, making the universe seem to expand faster here than it actually does elsewhere. It's like trying to measure the speed of a river's current while floating in a whirlpool. Your readings might not reflect the true flow. This isn't just a technical hiccup. If the void's low density distorts our measurements, it could mean the Hubble tension isn't a flaw in our models but a quirk of our cosmic address. Some simulations suggest that observers inside large voids would indeed calculate a higher Hubble constant, potentially explaining why local measurements clash with those taken from the universe's early glow. But not everyone's convinced. Critics argue that while voids influence local motion, their effect shouldn't be dramatic enough to account for the full discrepancy. The debate hinges on just how much the Great Void's gravitational emptiness ripples outward, warping our view of cosmic expansion. What's at stake goes beyond academic curiosity. If voids like this one are silently twisting our measurements, it could reshape our understanding of dark energy's power, or even hint that it's not as uniform as we thought. Alternatively, if the void's influence is minor, the Hubble tension might point to something far more radical. new physics, like a breakdown in Einstein's theory of gravity on cosmic scales. Either way, the Great Void isn't just a passive hole in space. It's an active player in one of cosmology's greatest puzzles, a reminder that where we stand in the universe might shape what we think we know about it. The irony is profound. The very emptiness that makes the Great Void so mysterious could also be the key to unlocking why our measurements of the cosmos seem so conflicted. As telescopes peer deeper into the void's edges and simulations grow more sophisticated, we might finally learn whether this cosmic oddity is a bystander or the missing piece in the puzzle of the universe's fate. Until then, the void stands as both a challenge and a clue, a silent force tugging at the fabric of our understanding. While the multiverse and dark energy dominate many discussions about the Great Void, some cosmologists are chasing even more radical ideas, theories that sound like they're pulled straight from science fiction. One of the most intriguing possibilities is that this cosmic emptiness isn't a void at all, but a scar from a cataclysmic event in the universe's infancy. Picture the early cosmos not as a smooth, uniform soup, but as a seething cauldron of phase transitions, moments when the very fabric of reality shifted states like water freezing into ice. If one of these transitions happened unevenly, it could have left behind pockets of frozen space-time, regions where matter never condensed properly. The Great Void might be one of these relics, a bubble of primordial chaos that never quite caught up with the rest of the universe. Then there's the quantum angle. At the smallest scales, particles flicker in and out of existence, creating a froth of fleeting energy fluctuations. Most of these cancel each other out, but what if, in the early universe, a particularly large quantum fluctuation got stretched to cosmic proportions during inflation? Imagine blowing up a subatomic hiccup to the size of a supervoid. It's like a single ripple in a pond growing into a tidal wave. This could explain the void's sheer size, not a gradual emptying of matter, but a primordial defect woven into spacetime itself. But perhaps the wildest theory involves primordial black holes, hypothetical monsters born not from collapsing stars, but from the intense pressures of the Big Bang. If enough of these ancient black holes clustered together, their combined gravity could have devoured nearby matter, clearing out a region over billions of years. Even more bizarre, some models suggest these black holes might not even be made of ordinary matter, but of dark matter or other exotic particles. If true, the Great Void wouldn't be empty, it'd be packed with invisible, ravenous giants lurking in the darkness. Not all these ideas are equally likely, but that's the point. The Great Void is so extreme that it forces scientists to think outside the box, to question whether our current models of physics are complete. Could it be evidence of extra dimensions where gravity leaks into other realms, or a cosmic string, a theoretical flaw in spacetime that sliced through this region long ago? Each hypothesis is a long shot, but in a mystery this profound, even the wildest guesses deserve a hearing. After all, history shows us that today's fringe theory might be tomorrow's breakthrough. The void's true explanation could be something no one has even imagined yet. What's remarkable isn't just the diversity of these theories, but what they reveal about science itself. When faced with the unknown, researchers don't just shrug and move on, they dream, they debate, and they dare to propose ideas that might seem absurd at first glance. The Great Void isn't just a hole in space, it's a playground for the imagination, a reminder that the universe still holds wonders beyond our wildest conjectures. And that's what makes it so thrilling, not just for scientists, but for anyone who's ever looked up at the night sky and wondered what else might be out there. Studying the Great Void is like trying to map a shadow. Its vast emptiness makes it nearly invisible to traditional telescopes, unlike galaxies or clusters which blaze with light, this cosmic desert offers little to observe directly. Astronomers can't just point a telescope at it and snap a photo. Instead, they've had to become cosmic detectives, piecing together clues from the void's subtle effects on its surroundings. One of their most powerful tools is the cosmic microwave background, the faint glow left over from the Big Bang. As light from this ancient radiation passes through the void, it undergoes tiny shifts in energy, a phenomenon called the integrated sachs-wolfe effect. These minuscule changes act like fingerprints, revealing the void's gravitational pull, or rather, its lack thereof. It's as if the void whispers its presence by bending light in ways that only the most sensitive instruments can detect. Another method involves painstakingly mapping the distribution of galaxies around the void's edges. By cataloging thousands of galaxies and measuring their redshifts, how much their light stretches as the universe expands, scientists can trace the outline of this cosmic whole. Think of it like reconstructing the shape of an invisible object by studying how dust swirls around it. But here's the catch. The Great Void is so enormous that even these galaxy surveys struggle to cover its full extent. It's like trying to survey the Grand Canyon with a flashlight. You might see fragments of the walls, but grasping the entire chasm requires stitching together countless observations. Then there's the challenge of perspective. From Earth, we're viewing the void through layers of cosmic clutter, galaxies, gas clouds, and other structures that can obscure or distort our measurements. It's akin to peering through frosted glass, where the true shape of what lies beyond is fuzzy and uncertain. To compensate, researchers use supercomputers to simulate the universe, comparing virtual voids to the real thing. These simulations help separate signal from noise, but they're only as good as the assumptions baked into them. If our models of dark matter or galaxy formation are even slightly off, the results could be misleading. Perhaps the biggest limitation is time. The Great Void scale means light from its far side takes hundreds of millions of years to reach us, offering a snapshot of the past, not the present. To understand how it's evolving, astronomers must rely on proxy data or wait for future telescopes to deliver sharper, deeper views. Projects like the Vera Rubin Observatory, with its panoramic gaze, promise to revolutionize this field. But for now, the void remains a puzzle wrapped in layers of cosmic uncertainty. What's remarkable isn't just the ingenuity required to study it, but the humility it demands. The Great Void reminds us that some of the universe's grandest mysteries aren't hidden in the glare of stars, but in the quiet, empty spaces between them. Light doesn't travel through the Great Void unchanged. It bends, stretches, and shifts in ways that betray the void's hidden influence. This peculiar behavior is known as the integrated sachs-wolfe effect, a cosmic quirk that turns the void into a natural laboratory for testing gravity itself. Here's how it works. As light from the cosmic microwave background, the afterglow of the Big Bang, passes through the void, it loses a tiny amount of energy. Not because something absorbs it, but because the void's gravitational pull, or rather, its lack thereof, alters the light's path. Imagine rolling a ball up a hill, only to find the hill has mysteriously flattened. The ball slows down, not because anything pushed it, but because the expected pull vanished. That's what happens to photons traversing this cosmic desert. They emerge slightly redder, their energy sapped by the void's weak gravity. This effect isn't just a curiosity, it's a clue. By measuring these subtle shifts, astronomers can map the void's gravitational fingerprint. In a universe where matter warps space-time, the Great Void's emptiness creates a kind of reverse gravity well. Instead of bending light inward like a galaxy cluster would, it lets light coast through relatively undisturbed, but with a telltale loss of energy. The result: a faint cold spot in the cosmic microwave background, a shadow cast by the void's absence. It's as if the universe left us a breadcrumb trail, a way to study this invisible giant by the marks it leaves on the oldest light we can see. What makes this especially fascinating is what it reveals about dark energy. If dark energy is accelerating the universe's expansion, it should weaken the gravitational pull of large structures over time, amplifying the integrated Sachs-Wolfe effect. The Great Void, with its staggering size, is the perfect place to test this. If the energy shifts here align with predictions, it could bolster the case for dark energy's role in cosmic evolution. But if they don't, that might hint at something even stranger, like flaws in Einstein's theory of gravity or unseen forces tugging at the fabric of spacetime. There's a catch, though. The effect is incredibly subtle, buried in noise from other cosmic signals. Detecting it is like listening for a whisper in a hurricane. Scientists must sift through mountains of data, separating the void's signature from distortions caused by interstellar dust, galaxy clusters, and even the motion of our own Milky Way. It's a testament to modern astronomy's precision that we can measure these shifts at all, yet even now, the data sparks debate. Some studies claim a strong detection, while others see only marginal hints. The void keeps its secrets closely guarded. What's clear is this: the Great Void isn't just empty space. It's a lens, bending our view of the cosmos in ways that challenge and refine our understanding of gravity, dark energy, and the universe's structure. Every photon that passes through it carries a message, one we're only just learning to decode. And as our tools grow sharper, the void's whispers may yet reveal answers to questions we haven't even thought to ask. The universe is full of voids, vast, empty regions where galaxies are few and far between. But not all voids are created equal. Take the Eridanus supervoid, a cosmic hole stretching over 1 billion light-years. At first glance, it dwarfs even the Great Void, but there's a catch. The Eridanus supervoid isn't completely empty. It's more like a cosmic sponge with scattered galaxies threading through its expanse. The Great Void, by contrast, is an almost pristine emptiness, a desert so barren it defies the usual rules of cosmic structure. Then there's the local void, right in our galactic backyard. This one's a modest 100 million light-years across, a pothole compared to the Great Void's canyon. Yet it's fascinating because we're practically sitting on its edge, giving astronomers a front-row seat to how voids shape the flow of galaxies around them. What sets the Great Void apart isn't just size, it's the sheer audacity of its emptiness. Most voids, like the Boötes Void, a close cousin to the Great Void, still cling to a handful of galaxies, like lone trees in a meadow. But the Great Void, it's more like a vacuum, with matter so sparse it's as if the universe forgot to fill in this corner. This extreme emptiness hints at something unusual in its formation. While most voids are thought to arise from natural underdensities in the early universe, the Great Void's scale suggests a more dramatic origin, maybe a collision with another universe, or a cataclysmic surge of dark energy that swept matter away like a cosmic broom. Comparing these voids is like studying footprints in the sand. Each one tells a different story about the forces that shaped it. The Eridanus supervoid's filamentary structure suggests it's a product of the cosmic web's gentle tug of war, where matter slowly drained away over eons. The local void, on the other hand, is actively pushing our Milky Way and its neighbors outward, like a bubble expanding in a pot of boiling water. But the Great Void, it's an outlier, a cosmic enigma that doesn't quite fit the mold. Its boundaries are sharper, its interior eerily quiet, as if nature hit pause on galaxy formation here. This comparison isn't just academic. By placing the Great Void alongside its cosmic siblings, we start to see patterns and anomalies. If most voids form through similar processes, why is this one so extreme? Is it a statistical fluke or evidence of a phenomenon we haven't yet imagined? The answers might lie not just in the void itself, but in the way it stands apart from the rest of the cosmic crowd. And that's what makes it so compelling, not as an isolated oddity, but as a piece of a much larger puzzle, one that's still waiting to be solved. To understand how something as vast as the Great Void could exist, we need to rewind the universe back to its earliest moments, a fraction of a second after the Big Bang. This was the era of cosmic inflation, when the entire cosmos underwent a growth spurt so violent it expanded faster than the speed of light. In less time than it takes to blink, the universe swelled from smaller than an atom to the size of a grapefruit, smoothing out wrinkles in spacetime while imprinting it with tiny quantum ripples. These microscopic fluctuations, random as they might have seemed, held the blueprint for everything we see today: galaxies, clusters, and yes, even voids like the Great Void. Picture inflation as a cosmic microscope, stretching those initial quantum jitters to astronomical scales. Where particles briefly clustered together, matter later condensed into galaxies. Where they thinned out, emptiness took hold. Most of these underdense regions grew into the modest voids we see scattered across the universe, but the Great Void. It's the cosmic equivalent of rolling a dozen sixes in a row. The sheer scale of its emptiness suggests an unusually large fluctuation got amplified during inflation, ballooning into this staggering void. It's like stretching a single grain of sand into a desert, an improbable, but not impossible, outcome of the universe's explosive youth. But here's where things get tricky. While inflation explains how voids could form, the Great Void pushes the theory to its limits. Most inflationary models predict a universe where matter is distributed fairly evenly on large scales, with no gaps as extreme as this one. Some scientists argue that the void's existence might mean inflation wasn't as uniform as we thought. Perhaps it happened in fits and starts, leaving behind patches of wildly different densities. Others suggest more exotic scenarios, like multiple rounds of inflation stacking the cosmic deck in favor of such anomalies. Then there's the question of timing. Inflation lasted just a sliver of a second, but its aftermath, the gradual growth of structures through gravity, took billions of years. For the Great Void to reach its current size, that initial fluctuation would have needed a head start, a slight edge over surrounding regions. Computer simulations struggle to replicate this. They can produce voids, but ones as vast and empty as the Great Void remain rare. This mismatch doesn't necessarily disprove inflation, but it does hint that our models might be missing a piece of the puzzle, something that allowed this void to grow unchecked while others stayed small. What's fascinating is how the void challenges us to rethink inflation's legacy. If it's truly a product of those primordial quantum fluctuations, then studying its properties could reveal secrets about the universe's birth that no telescope can see directly. The void becomes a time capsule, preserving clues about forces that vanished almost as soon as they appeared. But if inflation can't explain the void's extreme properties, that's equally revolutionary. It might mean our cosmic origin story needs rewriting. For now, the Great Void stands as both a testament to inflation's power and a thorn in its side. It's a reminder that even our best theories have edges, places where the universe refuses to follow the script. And that's what makes it so compelling, not just as a scientific mystery, but as a window into the forces that shaped everything we know. Supercomputer simulations are like cosmic time machines. They let us rewind the universe's history, tweak the rules of physics, and fast forward to see what unfolds. These digital universes, built on equations and powered by some of the world's most advanced machines, have become indispensable tools for cosmologists. They've successfully recreated the cosmic web's intricate filaments, the dance of galaxy clusters, and even smaller voids that dot the universe. But when it comes to the Great Void, the simulations hit a wall. No matter how many times scientists run the numbers, they can't seem to grow a void that matches its staggering scale and emptiness. It's like baking a cake with all the right ingredients, only to find it rises 10 times taller than the recipe promised. Something's clearly missing from the mix. One of the biggest hurdles is dark matter. Simulations rely heavily on this invisible scaffolding to shape the universe, letting gravity pull matter into the structures we observe. In most cases, this works beautifully. Dark matter's subtle clumps and streams guide galaxies into place, leaving behind voids of predictable sizes. But the Great Void's sheer vastness suggests that dark matter, at least as we currently model it, might not be the whole story. Perhaps its distribution in the early universe wasn't as smooth as we assume, or maybe an unknown interaction between dark matter and dark energy skewed the results. Some researchers have tried injecting boosted dark energy fluctuations into simulations, creating temporary surges that push matter away. These tweaks can produce larger voids, but they still fall short of the Great Void's extreme proportions. Then there's the problem of initial conditions. Simulations start with a snapshot of the early universe based on the cosmic microwave background's faint ripples. But what if those ripples aren't the full picture? The Great Void's existence hints that the infant cosmos might have had deeper underdensities, cosmic potholes that our current models overlook. It's like trying to predict a storm's path without knowing every gust of wind that shaped it. Without those missing pieces, even the most powerful supercomputers are working with an incomplete script. The discrepancies don't just frustrate scientists, they excite them. Every time a simulation fails to replicate the void, it's a clue that our understanding of cosmic evolution might need adjusting. Could there be a flaw in how we model gravity on the largest scales? Or is the void evidence of an exotic particle, something beyond dark matter, that played a role in shaping the cosmos? Some theorists have even proposed that the void's existence points to a bubble universe scenario, where our patch of the cosmos had slightly different physics than neighboring regions. While these ideas are speculative, they highlight how a single anomaly can shake the foundations of what we think we know. What's next? Scientists are refining simulations with ever higher resolution, adding finer details to the cosmic web structure. Upcoming projects like the Vera Rubin Observatory will deliver real-world data on millions of galaxies, giving simulators new benchmarks to aim for. The goal isn't just to recreate the Great Void, it's to discover whether it's a cosmic outlier or a signpost to a deeper truth. Because if there's one thing this void teaches us, it's that the universe is always more creative than our models can predict. And that's what makes the chase so thrilling, not just filling the gaps in our knowledge, but uncovering the gaps we didn't even know were there. The Great Void doesn't exist in isolation, it's part of a cosmic neighborhood, surrounded by structures that might hold the key to its origins. To the east lies the Boötes supercluster, a sprawling metropolis of galaxies that forms one of the densest regions in the observable universe. To the west, smaller voids and filaments weave through the cosmic web like threads in a tapestry. This contrast couldn't be starker. On one side, a bustling galactic city; on the other, an emptiness so profound it defies explanation. Scientists call this arrangement a void supercluster pair, and it's one of the most striking features of our local cosmos. But what does this juxtaposition tell us? One theory suggests that the Boötes supercluster might have played a role in draining matter from the Great Void over billions of years. Picture a cosmic tug of war where gravity acts as the rope. The supercluster's immense mass could have pulled galaxies and gas toward it, leaving the void increasingly empty. Over time, this process might have exaggerated the void's natural underdensity, turning it into the extreme anomaly we see today. It's like watching water rush downhill, leaving behind a dry basin. But here's the puzzle. If the supercluster siphoned matter from the void, why isn't the void smaller? Most gravitational interactions would shrink a region, not stretch it to hundreds of millions of light years. Then there's the possibility that the void isn't alone. Recent surveys hint that it might be part of a larger network of emptiness, a chain of voids stretching across the universe like bubbles in foam. If true, the Great Void could be just one link in a vast cosmic structure, shaped by forces acting on scales we're only beginning to map. This idea challenges the notion that voids are isolated oddities. Instead, they might be interconnected, forming a hidden skeleton beneath the visible universe. Studying the void's surroundings isn't just about filling in blanks on a map. The way galaxies move near its edges offers clues about dark matter's influence. Some galaxies skirt the void's border as if repelled by an invisible force, their paths curving away rather than drifting inward. Others seem to race toward the supercluster, caught in a river of cosmic motion. These dynamics suggest that the void isn't passive, it's actively shaping the flow of matter around it, like a rock diverting a stream. The Boötes supercluster adds another layer of intrigue. Its galaxies are older and redder than average, as if star formation there peaked long ago. Meanwhile, galaxies near the void's edge appear younger and bluer, their star-making factories still running strong. This mismatch hints that the void's environment might slow down galactic aging, like a cosmic fountain of youth. Or perhaps the supercluster's intense gravity stifled star birth long ago, leaving it a relic of an earlier era. What emerges from these observations is a picture of a dynamic, interconnected cosmos, where emptiness and density dance in an intricate balance. The Great Void isn't just a whole, it's a participant in the universe's grand choreography, its existence intertwined with the structures around it. And as astronomers piece together this cosmic puzzle, they're not just mapping space, they're uncovering the hidden forces that shaped everything we see. When faced with something as vast and mysterious as the Great Void, it's no surprise that human imagination runs wild. One of the most persistent myths is that this cosmic emptiness isn't natural at all, that it's the handiwork of an advanced alien civilization. The idea goes like this: a species far older than ours could have harnessed unimaginable energy to clear out an entire region of space, perhaps to build a Dyson sphere on a galactic scale or create a refuge from some cosmic threat. It's a compelling story, but the reality is far less dramatic. The sheer energy required to displace thousands of galaxies would defy the laws of physics as we know them. Even if such a civilization existed, nature offers a simpler explanation, one that doesn't require extraterrestrial architects. Then there's the notion that the Great Void is a gateway to another dimension, a cosmic wormhole left behind by some ancient cataclysm. This theory taps into our fascination with the unknown, suggesting that the void isn't empty at all, it's just hiding something beyond our perception. While wormholes are mathematically possible in Einstein's equations, they'd require exotic matter with negative energy to stay open, something we've never observed. More importantly, if the void were a portal, we'd expect to see bizarre gravitational lensing or energy fluctuations at its edges. Instead, it behaves like any other underdense region of space, just on an unprecedented scale. Some have even suggested the void is evidence of a parallel universe brushing against our own, a scar from a collision with another cosmic bubble. This idea borrows from legitimate multiverse theories, but there's a crucial difference. In scientific models, such collisions would leave distinct patterns in the cosmic microwave background, hot or cold spots with very specific shapes. The Great Void doesn't match those predictions. Its temperature fluctuations align with what you'd expect from a particularly large but otherwise ordinary void, not a bruise from another reality. Perhaps the most persistent misconception is that the Great Void threatens Earth somehow, that its emptiness is sucking in nearby galaxies or destabilizing our corner of the cosmos. In reality, voids don't exert some mysterious pull, they're just regions where gravity is slightly weaker. Galaxies near the void's edges might drift away over billions of years, but that's a gentle, imperceptible process, not a cosmic vacuum cleaner. The Milky Way is perfectly safe, separated from the void by hundreds of millions of light years and countless galactic neighbors. What's revealing about these myths is how they reflect our own biases. When confronted with the unknown, we tend to fill the gaps with familiar narratives, aliens, portals, hidden dangers, but the truth is often stranger than fiction. The Great Void doesn't need exotic explanations to be fascinating. Its very existence challenges our understanding of the universe in ways that are far more profound than any sci-fi scenario. It's a reminder that reality, when studied closely, is usually more surprising than anything we could invent. The Great Void isn't just a scientific curiosity, it's a cosmic mirror, forcing us to confront fundamental questions about our place in the universe. For centuries, the Copernican principle has been astronomy's guiding light, the idea that Earth holds no privileged position in the cosmos. We orbit an ordinary star in an unremarkable galaxy, one of billions in a universe that looks roughly the same in all directions. But the void's staggering size throws a wrench into this comforting assumption. When you're staring at a 330 million light-year hole in the cosmic web, it's hard to shake the feeling that we might be looking at something truly exceptional, and that perhaps our corner of space isn't so ordinary after all. This isn't just philosophical musing. The void's extreme nature suggests the universe might be far more uneven, far more unpredictable than the Copernican principle allows. Imagine standing in a forest where most trees are roughly the same height, then suddenly finding yourself at the edge of a clearing so vast you can't see the other side. That's the cognitive whiplash astronomers experience when studying the Great Void. It forces us to ask, are we seeing a statistical fluke, a 1 in a trillion anomaly? Or is this emptiness evidence that the cosmos has preferred structures, places where the rules of galaxy formation play out differently? The implications ripple outward. If the void challenges our assumption of cosmic uniformity, it also nudges us to reconsider life's place in the universe. For decades, the search for extraterrestrial intelligence has operated on the principle that life could arise anywhere with the right conditions. But what if habitable worlds cluster in certain regions, avoiding voids entirely? The Great Void's near-total lack of galaxies means fewer stars, fewer planets, and dramatically reduced chances for life to emerge. We might inhabit not just an ordinary galaxy, but a privileged pocket of cosmic real estate where matter and life could flourish. There's a humbling beauty in this realization. The void reminds us that the universe isn't just stranger than we imagine, it's stranger than we can imagine. Every time we think we've grasped its patterns, nature throws us a curveball. The Copernican principle isn't wrong, it's incomplete. We may not be at the center of the cosmos, but we're also not floating in a perfectly uniform soup of galaxies. We exist in a universe of extremes where vast emptiness and dazzling complexity exist side by side. Perhaps the most profound lesson lies in what the void represents, a frontier. Like ancient cartographers marking "Here be dragons" on unexplored regions of their maps, modern cosmologists face a similar unknown. The Great Void isn't just empty space, it's a question mark, a challenge to our understanding, and an invitation to keep exploring. In the end, it's not about whether we're special or ordinary, but about recognizing that the universe still holds mysteries waiting to reshape how we see ourselves within it. The next decade could bring us closer than ever to unraveling the Great Void's secrets, thanks to a new wave of telescopes designed to probe the cosmos with unprecedented precision. Leading the charge is the Vera Rubin Observatory, set to begin its 10-year legacy survey of space and time in 2025. With its 3.2 gigapixel camera, the largest digital camera ever built for astronomy, this Chilean-based powerhouse will scan the entire southern sky every few nights, capturing details previous surveys missed. Unlike telescopes that focus on specific targets, Rubin's wide-field view is perfect for mapping the void's true extent, potentially revealing faint galaxies or structures hidden within its emptiness that current instruments can't detect. But Rubin isn't working alone. The Nancy Grace Roman Space Telescope, launching around 2027, will combine Hubble's sharp vision with a field of view 100 times wider. Its infrared eyes will peer through cosmic dust, uncovering how the void interacts with surrounding galaxies on scales never before measured. Meanwhile, the Square Kilometre Array, the world's largest radio telescope now under construction, will trace the distribution of hydrogen gas, the universe's most abundant element, across the void's expanse. If dark matter or exotic particles left any imprint on this primordial gas, these radio waves might carry their signature. What makes these tools revolutionary isn't just their technology, but their synergy. Rubin will spot anomalies, Roman will examine them in high resolution, and the Square Kilometre Array will map the invisible scaffolding between galaxies. Together, they could answer fundamental questions. Does the void contain ultra-diffuse galaxies too dim for current telescopes? Are its edges sharper or fuzzier than simulations predict? And crucially, does it harbor any subtle patterns that might hint at its origins? The data won't just fill textbooks, it could rewrite them. If these observatories confirm the void's properties defy standard cosmological models, we might need to revisit everything from dark matter's behavior to inflation's legacy. Alternatively, if they find the void is less extreme than we thought, it could restore confidence in our current theories. Either way, the Great Void's days as a complete mystery are numbered. We're on the verge of seeing this cosmic oddity not as a blurry shadow, but in razor-sharp detail, and that could change how we understand the universe itself. Beyond hardware, new analysis techniques are turning existing data into fresh insights. Machine learning algorithms now sift through galaxy surveys, searching for overlooked patterns in the void's structure. Citizen science projects invite amateur astronomers to help classify unusual objects near its edges. Even gravitational wave detectors like LIGO might contribute. If the void's gravity distorts passing ripples in spacetime, it could offer an entirely new way to study its mass distribution. The most exciting possibility, these tools might uncover voids even larger and stranger than the Great Void, forcing us to confront whether it's truly unique or part of a hidden cosmic architecture. As the next generation of telescopes comes online, one thing is certain: the void won't stay silent for long. Its secrets, locked away for billions of years, are finally within our reach. When Robert Kirshner's team first unveiled the Great Void in the 1980s, the scientific community didn't just raise eyebrows, it split into camps. Some astronomers dismissed it as a statistical fluke, a cosmic illusion caused by gaps in their data. After all, the idea of a region 330 million light-years wide being nearly empty of galaxies seemed to defy everything they knew about the universe's large-scale structure. One critic famously compared it to finding a swimming pool in the middle of the Sahara possible, but so unlikely that you'd triple-check your measurements before believing it. Skeptics demanded more evidence, convinced that deeper observations would eventually fill the void with the missing galaxies. But as follow-up studies confirmed the void's existence, that skepticism gave way to fascination. Cosmologists began treating it like a puzzle box, each new observation adding another layer of intrigue. The Great Void wasn't just a curiosity, it was a challenge to the standard model of cosmology, a thorn in the side of theories that assumed matter was distributed relatively evenly across the universe. Conferences buzzed with debates. Was this a flaw in their understanding of dark matter, a sign of exotic physics, or simply a reminder that the cosmos thrives on outliers? The void became a Rorschach test for theoretical physicists, with everyone seeing different implications in its emptiness. Meanwhile, the public's imagination caught fire. News outlets latched onto the void's otherworldly scale, dubbing it the cosmic nothingness or the hole in the universe. Sci-fi authors spun tales of ancient alien megastructures or hidden dimensions lurking within its borders. Conspiracy forums lit up with theories that NASA was hiding the truth about its true purpose. Even religious groups weighed in, some interpreting the void as evidence of divine craftsmanship, a blank canvas in the celestial mural. This cultural frenzy wasn't just about the science, it was about what the void represented. In a world where humanity often feels small, here was something that made the universe itself seem stranger, more unknowable. The void's discovery also reshaped astronomy's priorities. Funding shifted toward large-scale galaxy surveys, with projects like the Sloan Digital Sky Survey dedicating unprecedented resources to map the cosmos in 3 dimensions. Researchers realized that if a void this colossal had gone unnoticed for so long, what else might be hiding in plain sight? The Great Void became a rallying cry for more ambitious observational campaigns, proving that the universe still had surprises up its sleeve. Perhaps the most enduring legacy of the void, though, was its humility lesson. For centuries, science had assumed the cosmos followed orderly, predictable rules. The Great Void reminded everyone that nature doesn't care about human expectations. Whether it's a statistical anomaly or a hint of deeper mysteries, its very existence whispers a truth that resonates beyond astronomy. The universe is under no obligation to make sense to us. And that's what keeps scientists and the rest of us looking up. The Great Void isn't just a scientific curiosity, it's a muse. From the pages of science fiction novels to the silver screen, this cosmic enigma has sparked creativity, tapping into something primal in the human psyche. Our fear of the unknown, our awe of emptiness, and our fascination with the infinite. Take the iconic novel The Void by science fiction writer Peter F. Hamilton. In his sprawling universe, the void isn't just an empty space, it's a sentient force, a cosmic entity that devours stars and civilizations. It's a metaphor for the unfathomable, a reminder that the universe might harbor intelligences so alien they're beyond comprehension. Hamilton's vision reflects our instinct to personify the void, to fill its emptiness with meaning, even if that meaning is terrifying. Then there's cinema. In the cult classic event Horizon, the titular spaceship doesn't just vanish into the void, it returns, haunted by something unspeakable. The void here isn't passive, it's a malevolent force, a hellish dimension where physics and sanity unravel. It's a trope that echoes Lovecraftian horror, the idea that vast, empty spaces might be anything but empty, that they could hide horrors beyond human understanding. Even blockbusters like Interstellar flirt with this idea. The film's portrayal of the black hole Gargantua owes a debt to the Great Void's mystique. Both are cosmic anomalies that defy logic, bending time and space in ways that feel almost supernatural. But not all depictions are ominous. In Star Trek Voyager, the crew encounters the Void, a region of space devoid of stars where survival depends on cooperation rather than conquest. Here, the Void becomes a blank slate, a place to test humanity's ideals. It's a refreshing counterpoint to the usual doom and gloom, showing how emptiness can also symbolize possibility, a canvas for reinvention. This duality, void as threat versus void as opportunity, reveals how deeply it resonates with our collective imagination. Beyond fiction, the great void has seeped into music and visual art. Ambient musicians like Brian Eno have crafted soundscapes meant to evoke the void's vastness, using drones and echoes to mimic its eerie silence. Visual artists, too, have tried capturing its scale, painting swirling abstractions or minimalist canvases dominated by negative space. These works don't just represent the void, they invite us to feel it, to confront the vertigo of standing at the edge of something so profoundly empty. Even video games get in on the act. Titles like No Man's Sky and Elite Dangerous let players traverse procedurally generated voids where the sheer loneliness of space becomes palpable. There's no soundtrack, no chatter, just the hum of your ship and the oppressive silence of the abyss. It's a gameplay choice that mirrors reality. The great void is silent, a place where radio signals fade and light stretches thin. By simulating that isolation, these games tap into the same awe that astronomers feel when they study the real thing. What ties all these portrayals together is their power to make the abstract tangible. The Great Void, for all its scientific intrigue, is hard to grasp intellectually, but art transforms it into something visceral, a monster, a mirror, a mystery. Whether it's fueling nightmares or inspiring wonder, one thing's clear: humanity can't resist the pull of the void. It's a blank screen onto which we project our deepest fears and wildest dreams, proving that even emptiness can be fertile ground for the imagination. Visualizing the great void is like trying to map the shape of the wind. You can't see it directly, but with the right tools, you can trace its influence across the cosmos. One of the most powerful instruments for this is the Sloan Digital Sky Survey's 3D Galaxy Map, a digital atlas charting millions of galaxies across billions of light years. Imagine zooming through this map, watching galaxies cluster into filaments and walls, then suddenly hitting the void's edge, where the vibrant cosmic web dissolves into eerie nothingness. The transition is so abrupt it feels like a glitch in reality, a digital artifact revealing just how unnatural this emptiness appears against the universe's bustling backdrop. For an even more immersive experience, researchers are now building virtual reality simulations that let you step inside the void, strap on a headset, and you're floating in a 360-degree abyss, where distant galaxies appear as faint pinpricks at the very limits of perception. Turn your head and you'll see the void's boundaries marked by a shimmering wall of galaxies, their collective glow tracing the outline of this cosmic cavern. These VR tools aren't just for show, they help scientists study galaxy flows around the void's edges, revealing how its gravity, or lack thereof, subtly bends the paths of nearby stars. It's like watching water spiral around a drain, except the drain is 330 million light-years wide. Then there's the Cosmic Web Imager, a data visualization tool that transforms dry numbers into dynamic art. Feed it redshift survey data, and it generates a swirling, color-coded tapestry where the Great Void emerges as a gaping indigo hole amid golden filaments. Adjust the parameters, and you can simulate how the void might have grown over time, watching as virtual matter flees its center like crowds evacuating a plaza. Some models even let you tweak dark energy's strength, showing how slight changes could inflate the void to even more mind-bending proportions or erase it entirely. But perhaps the most haunting visualization comes from sonification projects, where astronomers translate the void's properties into sound. Data points become musical notes, with denser regions producing higher pitches and the void's emptiness rendered as a sustained, hollow drone. The effect is unsettling, a cosmic symphony where one instrument falls silent for measures on end. It's a reminder that the void isn't just a visual anomaly, it's a disruption in the very fabric of the universe, perceptible through multiple senses. These tools do more than dazzle, they democratize discovery. Amateur astronomers can now explore the void from their laptops, while educators use these visualizations to spark curiosity in classrooms. When you can fly through the great void with a mouse click or feel its scale in VR, abstract cosmology becomes visceral. And that's the real magic, turning the universe's greatest mysteries into something you can reach out and touch, or at least virtually stand inside. The Great Void isn't just a scientific mystery, it's a battleground of ideas where cosmologists clash over what its emptiness truly means. On one side stand the skeptics, who argue it's nothing more than a cosmic coincidence. They compare it to finding an unusually large gap in a sand dune, statistically rare, perhaps, but not impossible in a universe as vast as ours. These researchers point to computer simulations that occasionally spit out similarly large voids, suggesting the Great Void might simply be the universe rolling a very lucky or unlucky die. Their mantra, extraordinary claims require extraordinary evidence, and until someone proves this void couldn't form naturally, they'll keep filing it under cosmic oddities rather than physics-breaking phenomena. But then there are the revolutionaries who see the void as a crack in cosmology's foundation. Led by thinkers like Laura Mersini-Horton, they argue its extreme size challenges the standard model of cosmic evolution. Imagine building a house where one wall inexplicably bows outward. You wouldn't shrug and call it a quirk. You'd question your blueprints. That's precisely what this camp is doing with our understanding of the universe. They highlight how the void scale strains inflationary theory, which predicts a relatively even distribution of matter on large scales. When your model says this shouldn't exist, but your telescope shows it plainly does, maybe it's time to revisit the model. The debate gets especially heated when dark energy enters the conversation. Some theorists propose that the void's existence hints at dark energy's uneven distribution, an idea that would upend decades of cosmological assumptions. Others counter that invoking special dark energy to explain one anomaly is like using a flamethrower to light a candle. The tension here isn't just academic, it cuts to how science progresses. Do we tweak existing theories to accommodate outliers, or do those outliers demand entirely new frameworks? Caught in the middle are the pragmatists who advocate for patience over paradigm shifts. They're the ones designing ever more sensitive galaxy surveys to determine if the void is truly as empty as it seems. Could there be faint, undiscovered galaxies hiding in its depths, or streams of dark matter we can't yet detect? This camp's motto might be measure twice, theorize once, emphasizing that before we rewrite physics textbooks, we'd better be certain we're not just seeing shadows on the cave wall. What makes these debates so fascinating isn't just the science, it's the human drama behind them. Careers have been built on defending or dismantling the void's significance. Conference Q and sessions turn into verbal jousting matches, with researchers wielding statistics like swords. Yet beneath the rivalry lies a shared excitement, a collective thrill at staring into the unknown. Because whether the Great Void ultimately proves to be a fluke or a revolution, it's already served its most important purpose, reminding us that the universe still has the power to surprise. Dark matter is the universe's invisible architect, an enigmatic substance that doesn't emit light, yet shapes the cosmos through gravity alone. We can't see it, but its presence is written in the way galaxies spin too fast to hold together, how light bends around empty space, and how the cosmic web forms its vast, intricate patterns. So when astronomers stare into the great void's staggering emptiness, one question looms large: could dark matter's hidden hand be responsible for carving out this cosmic chasm? The answer might lie in the early universe, where dark matter's clumpy distribution set the stage for everything that followed. Picture the infant cosmos as a simmering pot of soup, with dark matter swirling like thick broth. Most regions had slight density variations, tiny ripples that gravity amplified over billions of years, pulling matter into galaxies and clusters. But what if some regions started with far less dark matter, like thin patches in the cosmic stew? These underdense areas would struggle to attract gas and stars, growing into voids as expansion stretched them even emptier. The Great Void could be the ultimate expression of this process, a place where dark matter was so scarce that galaxies never got a chance to form. But here's the twist: dark matter isn't just missing from the void, it might be the reason the void exists at all. Simulations show that dark matter doesn't just sit passively, it acts like a cosmic sculptor, guiding where ordinary matter flows. In dense regions, its gravity herds gas into galaxies. In voids, its absence lets matter drift away like leaves on a wind. The Great Void's extreme emptiness suggests dark matter might have been unusually sparse here from the beginning, creating a gravitational dead zone where galaxies couldn't take root. Some models even propose that dark matter particles might interact with each other in ways we don't yet understand, perhaps pushing apart in the early universe, leaving behind bubbles of near-nothingness. Yet not all dark matter is created equal. Most theories assume it's cold, slow-moving and clumpy, which fits the cosmic web we observe. But if some dark matter were warm, moving faster and smoothing out small-scale structures, it could explain why the Great Void is so starkly empty. Warm dark matter would resist clustering on smaller scales, potentially creating broader, more uniform voids. It's a tantalizing idea, but there's a catch. Warm dark matter also struggles to explain how galaxies formed so early in the universe's history. The Great Void might be forcing us to reconsider not just where dark matter is, but what it fundamentally is. Then there's the wild card: what if dark matter isn't the only player? Some theorists speculate that the void scale hints at an interaction between dark matter and dark energy, two mysteries colliding. Imagine dark energy as a tide, ebbing and flowing unevenly across the cosmos. In the void's region, a surge might have pushed dark matter aside, weakening its gravitational pull and allowing ordinary matter to evacuate. It's like blowing across the surface of a cup of coffee. The darker liquid dark matter parts to reveal the lighter liquid the void beneath. If true, this would mean the Great Void isn't just a hole in the cosmic web, but a fossil record of an ancient tug of war between the universe's two most mysterious forces. The challenge, as always, is evidence. Dark matter's invisibility makes it maddeningly hard to map directly. Astronomers rely on indirect clues, like how the void's gravity bends light from distant galaxies, or how its edges distort the cosmic microwave background. These observations suggest dark matter isn't entirely absent from the void, just incredibly diffuse. It's like sensing the faintest breath of wind in an otherwise still room. There's something there, but barely. Future telescopes, like the Vera Rubin Observatory, could change the game by detecting ultra-faint galaxies or dark matter filaments threading through the void's emptiness. Until then, the Great Void remains a puzzle with dark matter at its heart, an unseen force that might hold the key to the universe's most striking emptiness. What's clear is this: the void isn't just an absence, It's a mirror reflecting dark matter's invisible influence, a place where the universe's hidden scaffolding is laid bare. Whether it's a relic of uneven distribution, a sign of exotic particle physics, or a cosmic battleground between dark forces, one thing is certain: the Great Void doesn't just challenge what we see. It challenges what we know about the unseen. The Great Void is more than a cosmic oddity, it's a masterclass in humility. For all our telescopes, supercomputers, and centuries of scientific progress, this staggering emptiness reminds us how much we still don't understand. The universe isn't a puzzle waiting to be solved. It's a living, evolving enigma that delights in defying expectations. Just when we think we've mapped the rules of cosmic structure, the void appears, a 330 million light-year rebuke to our assumptions. It's as if the cosmos is whispering, "You think you've seen it all, here's something you didn't account for." This humbling effect isn't unique to astronomy. History is littered with discoveries that upended what we thought we knew. Galileo's telescope revealed moons orbiting Jupiter, proving Earth wasn't the center of all motion. Hubble's observations showed galaxies receding, exposing an expanding universe. Now, the Great Void joins this legacy, challenging our belief that matter is spread evenly across the cosmos. Each of these revelations started with someone noticing an anomaly, a detail that didn't fit the narrative. The Void's lesson: progress often begins not with certainty, but with curiosity about the things that don't make sense. Yet there's a deeper, more personal dimension to this. Staring into the void forces us to confront our own insignificance in the grand scheme. Earth is a speck orbiting an average star, itself one of billions in a galaxy that's just one among countless others. And now we learn that even galaxies cluster unevenly, leaving voids so vast they could swallow our entire cosmic neighborhood without a trace. It's a perspective shift akin to realizing the ocean isn't just what's near the shore. Its trenches and abysses so deep they redefine what deep means. The void doesn't just expand our view of space, it recalibrates our sense of scale, both cosmic and personal. But humility isn't the same as futility. The void's mystery isn't a dead end, it's an invitation. Every unanswered question is a frontier, a call to build better telescopes, refine theories, and train the next generation of scientists. After all, the most exciting phrase in science isn't "Eureka." But that's funny. The Great Void is the ultimate funny observation, a cosmic wink nudging us to look harder and think deeper. It proves that wonder isn't reserved for childhood. It's woven into the fabric of reality, waiting to be rediscovered with each new discovery. Perhaps the most profound lesson is this: the universe owes us no explanations. It doesn't care if its structures fit our models or if its scale strains our imagination. The Great Void exists whether we comprehend it or not, a silent testament to nature's indifference to human expectations. And that's oddly liberating. It means there will always be mysteries to chase, horizons to push. In a world where so much feels known and mapped, the void is a reminder that wonder still lives, out there in the darkness, in the gaps between the stars, in the questions we haven't even thought to ask yet. The Great Void might be one of the most baffling cosmic mysteries, but it's far from alone in the universe's catalog of oddities. Take fast radio bursts, those split-second blasts of energy so powerful they outshine entire galaxies, yet vanish without a trace. These cosmic flashes appear randomly across the sky, lasting just milliseconds, but pack more energy than the sun emits in decades. Some repeat like clockwork, others fire once and never again. Scientists have proposed everything from colliding neutron stars to alien megastructures as explanations, but the truth remains elusive. Like the Great Void, these bursts defy easy categorization. reminding us that the cosmos loves to keep us guessing. Then there are rogue planets, worlds untethered to any star, drifting through interstellar space like cosmic nomads. Unlike Earth, which basks in the sun's warmth, these lone wanderers float in perpetual darkness, their surfaces frozen to near absolute zero. Yet some might harbor hidden oceans beneath icy crusts, kept liquid by tidal forces or radioactive decay. The idea that life could exist in such extreme environments challenges our Earth-centric view of habitability. Just as the Great Void upends assumptions about cosmic structure, rogue planets force us to rethink where and how life might thrive. But perhaps the strangest cousin to the Great Void is the Boötes Void's own smaller sibling, KBC Void, a recently discovered emptiness that makes our galactic neighborhood feel like a lonely outlier. While the Great Void spans 330 million light-years, the KBC Void envelops the Milky Way itself, stretching over 2 billion light-years. We're floating near its edge like a speck of dust clinging to the rim of a colossal drain. This realization flips the script on cosmic geography. Instead of residing in a bustling metropolis of galaxies, we might be perched on the fringe of one of the universe's largest known voids. Even more enigmatic are cosmic filaments, threads of dark matter and gas stretching billions of light-years, connecting galaxy clusters like beads on a string. The Hercules Corona Borealis Great Wall, one of the largest structures ever observed, dwarfs the Great Void entirely, spanning 10 billion light-years. Its existence strains the cosmological principle, which states that the universe should look roughly the same no matter where you're standing. Finding a wall this massive is like discovering a mountain range so tall it shouldn't fit on the planet, except the planet is the observable universe. What ties these anomalies together isn't just their strangeness, it's how they reveal the universe's flair for breaking its own rules. The Great Void's emptiness, fast radio bursts, fleeting fury, rogue planets' solitary journeys, they all whisper the same truth. The cosmos is far wilder than our textbooks dared to suggest. Every time we build a model to explain how things work, the universe tosses us a curveball, grinning as we scramble to make sense of it. And that's the real magic, not just the mysteries themselves, but the way they keep us humble, curious, and forever staring skyward. To trace the Great Void's timeline is to step into a cosmic detective story, where clues are buried in the faint glow of ancient light and the silent drift of galaxies. Let's rewind to the universe's fiery infancy, mere moments after the Big Bang. In that searing chaos, quantum fluctuations, tiny ripples in the fabric of space-time, were the seeds of all future structure. Most of these ripples were minor, but the Great Void's staggering scale suggests it sprouted from an exceptionally rare underdensity, a patch of the primordial cosmos where matter was sparser than the surrounding soup. As inflation stretched the universe exponentially, that tiny deficit ballooned into a vast emptiness, a bubble of near-nothingness adrift in a sea of potential. Fast forward several hundred million years to the era when the first galaxies flickered to life. While dense regions of the cosmic web lit up with newborn stars, the void's emptiness left it in darkness. Without enough matter to collapse into galaxies, it became a cosmic desert, not by some cataclysmic evacuation, but by default. Gas here was too thin to ignite star formation, leaving the void a shadow against the growing brilliance of the universe. Over eons, as galaxies elsewhere clustered into superclusters and filaments, the void's boundaries sharpened. Gravity, which builds structure elsewhere, played a different role here. It didn't just fail to attract matter. It allowed expansion to stretch the void even emptier, like taffy pulled thin until it nearly disappears. By the time the universe reached half its current age, the Great Void had settled into its modern identity, a titanic cavity fringed by galaxy-rich walls. But it wasn't static. Dark energy's accelerating grip on the cosmos began to dominate, and the void's expansion subtly shifted. Without the gravitational tug of matter to resist it, dark energy's push became more pronounced here than in denser regions. The void didn't just grow, it grew faster, its edges stretching away from the surrounding cosmic web like a rubber sheet tearing at its seams. This acceleration might explain why the void's emptiness is so extreme today. It's not just a relic of the past, but a structure still evolving under dark energy's influence. Yet mysteries linger. Why hasn't the void filled in, even slightly, over billions of years? Simulations suggest that smaller voids often get swept up by larger structures, their emptiness diluted by infalling matter. But the great void's persistence hints at something more profound, perhaps a self-reinforcing cycle where its lack of gravity repels potential settlers, like a cosmic exclusion zone. Light from distant galaxies passing through the void offers snapshots of its history, revealing how its gravitational shadow has deepened over time. Each photon that traverses this emptiness carries a record of its journey, a diary of the void's growth written in redshift and deflection. The most tantalizing question isn't just how the void formed, but what it's becoming. As the universe's expansion accelerates, the void's fate may diverge dramatically from the rest of the cosmos. In tens of billions of years, it could stretch so wide that galaxies on its far side vanish beyond the horizon of observation, leaving future astronomers, if any exist, with no clue it was ever there. The Great Void's timeline isn't just a chronicle of the past. It's a preview of cosmic isolation on a scale we're only beginning to fathom. And that's the irony. This emptiness, so ancient and immense, might one day be the universe's last testament to the structures we once thought eternal. Detecting something as vast yet invisible as the Great Void requires tools that push the boundaries of modern astronomy. Gone are the days of relying solely on optical telescopes to scan the night sky. Today's void hunters wield an arsenal of technology so advanced it feels like science fiction. Take radio telescopes like the Atacama Large Millimeter Array, or ALMA, nestled high in Chile's desert. Unlike traditional telescopes that capture visible light, ALMA 66 precision antennas tune into millimeter waves, revealing cold gas and dust invisible to other instruments. This lets astronomers map the void's edges with unprecedented detail, spotting faint trails of matter that hint at how galaxies were or weren't able to form in this cosmic desert. But the real game changer, artificial intelligence. Machine learning algorithms now sift through petabytes of data from projects like the Sloan Digital Sky Survey, identifying patterns human eyes would miss. Imagine training an AI to recognize the subtle gravitational distortions caused by the void's emptiness, like teaching it to spot the wake of an invisible ship passing through water. These programs analyze galaxy distributions, redshift measurements, and even the cosmic microwave background, flagging anomalies that could signal hidden voids or unexpected structures within them. Some AIs go further, simulating millions of cosmic scenarios to predict how voids evolve, offering clues about the great void's past and future. Then there's gravitational lensing, a technique that turns the universe itself into a magnifying glass. When light from distant galaxies passes near the void, its path bends ever so slightly, a distortion caused by the void's weak but measurable gravity. Instruments like the Hubble Space Telescope and the upcoming Nancy Grace Roman Telescope capture these minute deflections, allowing scientists to weigh the void's emptiness. It's like diagnosing a patient by observing how their shadow falls, except the patient is a billion light-year-wide pocket of spacetime, and the shadow is the warped light of galaxies billions of years old. Perhaps most revolutionary are the multi-messenger approaches that combine data from disparate sources. Astronomers now cross-reference observations from gamma-ray telescopes, neutrino detectors, and even gravitational wave observatories like LIGO, searching for correlations that might explain the void's origins. Could a burst of ancient gamma rays have cleared this region, or does the void's gravity subtly alter passing gravitational waves? By stitching together these disparate threads, researchers build a fuller picture of the void's influence across the electromagnetic spectrum and beyond. The future looks even brighter. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time will scan the entire southern sky every few nights, spotting transient events near the void that might reveal its dynamics. Meanwhile, the square-kilometer array's thousands of radio dishes, set to come online in the next decade, will map hydrogen gas distribution with enough precision to trace how matter flows, or doesn't, into the void's depths. These tools aren't just incrementally better, they're rewriting the rules of cosmic exploration, turning what was once an impenetrable mystery into a frontier ripe for discovery. What's thrilling isn't just the technology itself, but how it democratizes science. Citizen scientists can now comb through void data via platforms like Zooniverse, classifying galaxies or flagging anomalies from their home computers. Even high school students contribute, training AI models or analyzing public datasets. The Great Void, once the domain of elite astronomers, is becoming a collaborative puzzle, one that anyone with curiosity and an internet connection can help solve. Yet for all these advances, the void retains its secrets. Each new tool reveals deeper layers of complexity, from unexpected galaxy distributions at its fringes to peculiar temperature fluctuations in the cosmic microwave background. The lesson is clear: as our technology evolves, so too does our understanding of just how much we don't know. The Great Void isn't just a target for our instruments, it's a mirror reflecting the ingenuity and persistence of those who dare to study it. The Great Void isn't just a mystery for professional astronomers, it's a gateway, a cosmic classroom where students and stargazers alike can grapple with the universe's biggest questions. Imagine a high school physics class not just memorizing equations, but debating how a region 330 million light-years wide could end up nearly empty. That's the power of this cosmic oddity. It turns abstract concepts like dark energy and cosmic inflation into tangible puzzles anyone can explore. Museums and planetariums are already capitalizing on this, with interactive exhibits that let visitors fly through the void in 3D, feeling its scale in a way textbooks can't convey. These experiences don't just teach facts, they spark the kind of awe that turns casual curiosity into lifelong passion. One of the most exciting developments is how citizen science projects are harnessing the void's allure. Platforms like Zooniverse invite amateur astronomers to help classify galaxies near the void's edges, contributing to real research while learning how cosmologists map the universe's structure. It's a far cry from rote memorization. It's hands-on discovery, where a teenager in Tokyo or a retiree in Buenos Aires might spot a faint galaxy everyone else missed. The Great Void becomes more than a lesson. It's a collaboration, proof that scientific progress isn't just for labs and universities. Even coding boot camps use void simulations to teach programming, challenging students to visualize cosmic data in creative ways. The message is clear: space isn't just something you read about, it's something you do. Teachers are finding ingenious ways to bring the void into classrooms. A middle school in Norway built a scale model of the cosmic web using yarn and beads, with the Great Void represented by an empty hula hoop. a visceral reminder of how much emptiness shapes the universe. University professors use it to illustrate the scientific method, showing how Kirshner's team went from "that's weird" to "this changes everything." The void's very resistance to easy explanation makes it perfect for teaching critical thinking. There's no textbook answer yet, so students can't just regurgitate facts. They have to weigh evidence, debate theories, and embrace uncertainty, just like real scientists. Beyond schools, the void is bridging gaps between science and art. A composer in Iceland created a symphony based on the void's redshift data, translating its emptiness into haunting chords. Visual artists use it as a metaphor for creativity itself, the blank canvas where new ideas emerge. Even sci-fi writers partner with astronomers to craft stories grounded in real cosmology, where the void isn't just a plot device but a character shaped by physics. THESE Chinese letter collaborations do more than entertain. They redefine who gets to engage with science. You don't need a PhD to wonder about the void. You just need imagination. Perhaps the void's greatest educational gift is its humility lesson. In a world where kids are bombarded with quick answers, the void reminds us that some mysteries endure. A fifth grader can ask, "Why is it there?" And the honest response is, "We're still figuring that out." That vulnerability, the admission that even experts don't know everything, can be liberating. It tells young minds that science isn't a static set of facts, but an ongoing conversation they can join. When a student realizes the same questions puzzling NASA might one day land on their desk, the universe stops being distant and becomes personal. The Great Void isn't just inspiring future scientists, it's reshaping how we all see our place in the cosmos. When we pour millions of dollars into studying the Great Void, it's worth asking what gets left behind. Astrophysics funding isn't infinite, and every telescope pointed at cosmic emptiness is one that isn't searching for habitable exoplanets, tracking near-Earth asteroids, or probing the origins of life. The ethical dilemma here isn't just academic. It's about balancing humanity's thirst for knowledge with the very real needs of our species. Some argue that voids, as extreme laboratories of cosmic evolution, deserve top priority. They challenge our fundamental theories in ways no other phenomena can. But others counter that focusing on distant abstractions while Earth faces climate crises and resource shortages feels like rearranging deck chairs on the Titanic. The debate gets even thornier when you consider who benefits from this research. Cutting-edge cosmology relies on billion-dollar facilities like the James Webb Space Telescope, often funded by taxpayers in wealthy nations. Meanwhile, communities a few miles from these observatories might lack basic scientific infrastructure. There's an uncomfortable asymmetry when a single void detection algorithm costs more than a rural school district's annual budget. Advocates for equitable science funding ask, shouldn't we address earthly inequalities before mapping cosmic ones? Yet there's a counterpoint. Investing in fundamental research has historically sparked unexpected breakthroughs, from GPS to medical imaging, that eventually benefit everyone. The Great Void might seem esoteric today, but the technologies developed to study it could seed tomorrow's revolutions. Then there's the question of urgency. Unlike climate science or pandemic preparedness, cosmic voids aren't exactly time-sensitive. The Great Void isn't going anywhere. It's persisted for billions of years and will likely outlast humanity. So why rush? Proponents of void research argue that understanding the universe's structure isn't just about satisfying curiosity. It's about preparing for our species' long-term survival. If we ever hope to traverse interstellar distances, we'll need mastery over cosmic geography, including the emptiest regions. Voids might one day serve as highways for generation ships, their lack of obstacles enabling safer travel. In this light, studying them isn't indulgence, it's foresight. Yet the most compelling ethical argument might be about perspective. The Great Void forces us to confront our place in a universe that doesn't revolve around us. In an era of nationalism and short-term thinking, that cosmic humility could be its own kind of gift. When schoolchildren learn that our galaxy floats near the edge of a void so vast it defies comprehension, it doesn't just teach physics, it fosters awe, unity, and a sense of shared wonder. That intangible benefit, hard as it is to quantify, might justify the investment all on its own. After all, a civilization that stops looking up risks forgetting how to move forward. At the edges of the Great Void, something extraordinary unfolds, a cosmic tug of war between emptiness and creation. Picture a shoreline where ocean waves meet sand, carving intricate patterns with each ebb and flow. The void's boundaries function similarly, but instead of water, it's gravity shaping the fate of galaxies. Where most of the universe's matter clusters into dense filaments, the void's extreme underdensity creates a stark contrast, like a vacuum sucking at the edges of existence. This imbalance doesn't just leave a blank space, it actively sculpts the galaxies that dare to form along its borders, warping their evolution in ways scientists are only beginning to understand. Take galaxy clusters like those in the Boötes supercluster pressed against the void's outer rim. These galaxies aren't just neighbors, they're survivors clinging to the fringe of an abyss. Without the gravitational pull of a dense environment, their gas reservoirs behave differently. In crowded regions, galaxies constantly collide, triggering bursts of star formation. But here, in the void's shadow, interactions are rare. Gas drifts more lazily, collapsing into stars at a slower, more measured pace. The result, galaxies here tend to be smaller, quieter, and oddly isolated, like desert oases starved of rain. Some even appear undernourished, with fewer heavy elements forged in stellar explosions, because the void's emptiness limits how often stars can be born and die to enrich their surroundings. But the void's influence goes deeper than just stunting growth. It might also alter galactic architecture. Simulations suggest that galaxies near voids often develop lopsided structures, their spiral arms stretching unevenly toward denser regions like plants leaning toward sunlight. This void-induced asymmetry could be gravity's way of compensating for the void's pull, or rather, its lack thereof. Without the balanced gravitational forces found in galaxy-rich environments, these edge-dwellers evolve in isolation, free from the chaotic mergers that shape their urban counterparts. It's a galactic nature versus nurture experiment on a cosmic scale, with the void acting as the ultimate control group. Then there's the dark matter factor. While the void itself is eerily empty, its outskirts might harbor diffuse halos of dark matter, invisible scaffolding that could funnel gas into galaxies in unexpected ways. Some models propose that these halos act like cosmic sieves, filtering ordinary matter into thin streams that feed star formation at the void's edges. Others argue the opposite, that dark matter's uneven distribution here stifles galaxy growth, leaving behind failed galaxies that never quite ignite. The truth might lie somewhere in between, with the void creating a Goldilocks zone, not too dense, not too empty, where galaxies form under conditions unseen elsewhere in the universe. The most tantalizing possibility, the Great Void could be a time capsule, preserving galaxies in an early state of evolution. In the crowded heart of galaxy clusters, fierce competition for resources leads to rapid, violent transformations. But the void's quiet frontiers might host galaxies that evolve slowly, like biological isolates on a remote island. Studying these galactic hermits could reveal how all galaxies behaved in the universe's youth before cosmic cities arose. It's as if the void has frozen a piece of cosmic history at its edges, offering astronomers a living museum of primordial galactic life. Yet for all its influence, the void isn't a one-way street. Galaxies at its edges might be shaping the void as much as it shapes them. As they eject gas through supernova winds or active black holes, these outflows could push against the void's boundaries, subtly enlarging its emptiness over billions of years. It's a feedback loop of cosmic proportions. The void molds the galaxies, and the galaxies, in turn, sculpt the void. This dance between presence and absence, between something and nothing, might hold the key to understanding not just this one anomaly, but the delicate balance that governs the entire universe. What emerges from this interplay is a humbling realization. Emptiness isn't passive. The great void isn't just a hole in the cosmic web. It's an active participant in the universe's story, a force that bends the rules of galaxy formation to its will. Its edges are laboratories of extreme astrophysics, places where the familiar laws of cosmic evolution twist into something new and unexpected. And as telescopes peer deeper into these frontier zones, they're not just mapping the void's borders, they're uncovering the invisible hand that shapes everything around it, one galaxy at a time. What if the great void isn't just an empty region of our universe, but a cosmic fingerprint left by something beyond it? Some theorists propose an idea straight out of science fiction, that this staggering emptiness might be the scar of a collision with another universe. Imagine two soap bubbles floating in a froth of higher dimensional space, each representing a separate cosmos with its own laws of physics. If they brushed against each other in the distant past, the energy released could have pushed matter away from the contact point, leaving behind a void in our universe's structure. This isn't pure fantasy. It's grounded in the mathematics of brain cosmology, a branch of string theory that suggests our universe might be a three-dimensional brain floating in a higher dimensional bulk. A collision with another brain could explain the void scale not as a random fluctuation, but as a deliberate mark, like a dent in a car fender after a fender bender. The implications are staggering. If the void is indeed a multiverse relic, it would be the first tangible evidence that other universes exist beyond our own. But proving it is another matter. Unlike a car crash where skid marks and debris tell the story, a collision between universes would leave subtler clues, perhaps subtle temperature variations in the cosmic microwave background, or peculiar gravitational waves with patterns unlike anything produced by black holes or neutron stars. Some researchers are scouring existing data for these fingerprints, while others are refining models to predict what such a collision would look like. The challenge is separating these signals from the cosmic noise, like trying to hear a whisper in a hurricane. Then there's the quantum angle. In the early universe, quantum fluctuations were stretched to cosmic scales during inflation, seeding the structures we see today. But what if some of those fluctuations weren't random? A radical idea gaining traction is that the great void might be a quantum bubble, a region where the vacuum energy of space briefly dropped to an unusually low value. Think of it like a pot of boiling water. Most bubbles are small and uniform, but occasionally a giant one forms due to a rare confluence of conditions. In this scenario, the void isn't a collision scar but a cosmic accident, a place where the quantum foam of spacetime itself briefly hiccuped, leaving behind a bubble of altered physics. Even wilder is the notion that the void could be a universe fossil, a remnant of a previous cosmic cycle. Some models of cyclic cosmology suggest the universe undergoes endless cycles of expansion and contraction, with each big bang preceded by a big crunch. In this view, the great void might be a relic of a previous iteration, a pocket of spacetime that somehow survived the reset, carrying echoes of a universe that existed before our own. It's like finding a prehistoric insect preserved in amber, except the amber is the fabric of reality itself. Of course, not all speculative theories are so grandiose. Some physicists argue the void could simply be a statistical outlier, a 1 in a trillion fluke in an otherwise uniform cosmos. After all, if you roll a die enough times, you'll eventually get a string of ones. In a universe as vast as ours, even the most improbable configurations can emerge purely by chance. But here's the catch: the void scale strains even this explanation. Most cosmic voids are around 100 million light-years across, manageable within standard models. The Great Void is more than 3 times that size, pushing the limits of what random can plausibly explain. What unites these theories, from multiverse collisions to quantum bubbles, is their ability to stretch our imagination. The Great Void forces us to confront the possibility that our universe might be stranger, messier, and more interconnected than we ever dared to dream. Whether it's a window into other realities or just a cosmic roll of the dice, one thing is certain: the void isn't just empty space. It's a question mark, a challenge to our understanding, and perhaps the first clue to a truth far beyond our current grasp. The Great Void stands as a humbling monument to the universe's endless capacity to surprise us. Think about it. Here we are, a species that's mapped the human genome, split the atom, and sent probes beyond our solar system. Yet this colossal emptiness defies every explanation we throw at it. It's not just a gap in space, it's a gap in our understanding, a cosmic shrug that reminds us how much lies beyond the edges of our knowledge. From the moment Robert Kirshner's team stumbled upon it in the constellation Boötes, this void has been more than a scientific curiosity. It's become a mirror reflecting the audacity of human curiosity. Consider everything we've explored: the multiverse theories that paint it as a collision scar, the dark energy models that suggest it's a cosmic pressure bubble, even the wild quantum hypotheses that imagine it as a frozen ripple from the birth of spacetime. Each explanation feels like a flashlight beam sweeping across a cavern, illuminating fragments without ever revealing the whole, and that's the beauty of it. The void isn't just a problem to solve, it's an invitation to keep questioning, to stay restless in our pursuit of the unknown. What's remarkable isn't just the void itself, but how it's reshaped science in its wake. It's forced astronomers to revisit century-old assumptions about the universe's uniformity, inspired engineers to build telescopes capable of seeing the invisible, and even sparked debates about whether we're missing entire chapters of cosmic history. The void's silence, its sheer refusal to fit neatly into our models, has spoken volumes about the flexibility and resilience of the scientific process. When faced with the inexplicable, we don't shut down, we double down, and let's not forget the cultural ripple effects. This emptiness has haunted novels, fueled conspiracy theories, and even inspired symphonies, proof that science's greatest mysteries don't stay confined to labs and lecture halls. They seep into our art, our philosophy, the way we see our place in the cosmos. The void isn't just a subject for astronomers, it's a shared human experience, a reminder that wonder doesn't require answers. So where does that leave us at the threshold, really? The next decade's telescopes, Rubin, Roman, the square-kilometer array, are poised to peel back another layer of the mystery. Maybe they'll find ghostly galaxies hiding in the void's depths, or patterns in the cosmic microwave background that hint at forces we've never imagined. Or maybe, just maybe, they'll deepen the mystery further, revealing complexities we can't yet fathom. Either outcome would be a triumph, because the void's greatest gift isn't closure, it's the promise that the universe still has stories left to tell. As we wrap up this journey, I'll leave you with a thought from Carl Sagan. Somewhere, something incredible is waiting to be known. The Great Void embodies that spirit. It's not a dead end, it's a doorway, and whether you're a seasoned astronomer or someone who just loves staring at the night sky, that doorway is open to all of us. So keep looking up, keep asking questions, and most importantly, keep wondering. The cosmos is vast, strange, and far from finished surprising us. If you've enjoyed this dive into the depths of nothingness, hit that like button, subscribe for more cosmic adventures, and drop your wildest void theories in the comments. After all, the next big discovery might just start with a conversation. Until next time, stay curious.